Hi, everybody. This is Mr. Very here, and this is the Lesson 5, Unit 1, Sections 1.10 and 1.11 lesson. So we're going to start with a warm-up. I'm going to be doing a 5-second countdown to remind you to pause the video to try the question on paper first before I reveal the answer. So be ready when you hear the 5-second countdown to pause it before you just get fed the answer. You have to try things on your own. Okay, I'm going to answer the Padlet questions for 1.10 and 1.11 topic questions, and then you guys are going to do the Delta Math classwork, and the AP Classroom assignment is posted. Remember, you need to complete that, and if you do not complete that, then you need to complete it with a free response answer and submit it on Google Classroom. So that only happens if you miss the assignment's due date, which is Monday the 28th at 8 p.m. So the exit ticket is technically due today. So that's going to be something I'll look through. And the exit ticket 1.10 and to 1.13 is assigned. And you will have all the skills necessary for that, even though 1.13 happens to be part of the asynchronous lesson, which is going to be assigned on Friday. So you should still be able to do that exit ticket. Okay? So with that said, let's start our warm-up. So please try this warm-up. I'm going to read it, and then I'm going to give you a chance to pause it. So the graph of the function f of x is shown below. State all values of x in the open interval from -9 to 9, for which the function has a removable discontinuity. So please go ahead and try this question. Please pause it. 5, 4, 3, 2, 1. All right. So remember, a removable discontinuity looks like this. It's either this type of thing or, I don't know, something like this, with a point put somewhere else. So a point is literally removed. The limit from the left or right still matches. So the limit overall matches as you push x to this x value. But the point could either be put somewhere else, vertically above or vertically below, or the point could be removed altogether. In both cases, the limit does not equal the function value. So the function value f of this x value would be this point. So of course, that limit is not equal to that. And of course, this one over here, the point isn't even there. So of course, the limit, which does exist, will not equal the function value. So of course, you can see there's 1, 2, 3, 4 of these. Okay, so let's move on to the next slide. So the answer was x equals -5, -3, 4, and 6. The reason it wasn't here is these are all jumps. This is a jump. This is a jump. Even both of these are holes. It's a jump. So these are all removable. The limit does not equal, the limit exists and does not equal the function value. So that's pretty much the reason. All right, good warm up. Moving on. Here are the Padlet questions. So let me read through them. Can you go over how to graph a piecewise function on our calculators? I love these calculator questions that students have. I'll always try to answer them with a complete response. So I just Googled our YouTube a video. So this video is about 8 minutes long. You really only need to watch the first few minutes. And you can scan this QR code here with your phone. And it's just either you can pull up your camera usually and just hover over it and the link should pop up to click. And then, or you can download a QR reader app, either way, or last resort, type in that horrible link, the long link. Number 2, can you explain the answer to the last question in the AP video 1.10? Absolutely, I can. The only thing is you didn't indicate a timing, which might have really helped mitigate this. I don't know exactly what you're talking about. And you needed to be a little more specific because that question has 4 parts. It's number 4 and it has 4 parts. So I don't know necessarily what part you're talking about. So just please, when you put these Padlet questions up, be as specific as you can. Number 3 says, can you explain why an infinite discontinuity is still continuous for its domain? I do get a good sense of what you're talking about. Again, indicating exactly where in a video. I can just jump right to there, and that would be better. Okay, so those are in there as slides somewhere. So we're going to come up to these questions in this presentation. So this, of course, this is question 2 right here. So of the Padlet questions. So this student was asking about the question for the last question. So which of the following is or are continuous on the domain? Okay, so basically the ones that are not going to be continuous on their domain are those removable ones where the point is put somewhere else. Okay, basically these piecewise functions cause this situation to happen. So none of these last 3 are continuous on their domain, but A certainly is. Now, the reason is because as we approach 5 from the right or left, right, we're going to go to infinity. So all of those points have a right and a left, every single one. 5.000000, 100 more zeros, 1. That's super close to 5. They're still closer. So that has a right or a left. So the limit exists, and the function value is the same as that limit. That's what continuity is all about. Okay, so at 5, well, 5 is not in question because it's not in the domain. So that vertical asymptote means that 5 isn't there. Now, had a point been put somewhere, it would have been a piecewise function. Those piecewise functions, all of these would, this one's not a piecewise function as it looks. It doesn't look like it is anyway, but because this one could be represented with one function, likely, that's A. These other ones have to be piecewise functions. So that means that there's, in this one, there looks like 3 parts to the piecewise. This one, there's 2 parts, and this one, there's probably 2 parts, right? So these are kind of all those situations. So the other thing is the domain cares about, is there just an output when I put that X value in? So let me go ahead and make a vertical line here, and I'm going to select it, and I'm going to slide it over. Look, this one here goes through, and there's a right and a left, and then the moment it doesn't, right here, that's not in the domain. Then it goes through everything again. This one here, literally every time, even at 5, this goes through the graph. It goes through a point that's on this part of this piecewise. And then this one, 5 is not in the domain, but this is not continuous. Well, technically, I guess we could say it's continuous on its domain, but at these considering endpoints are definitely not continuous, but 5 is not in question. So technically this is continuous on its domain, and this one is not continuous on its domain because 5 is there. Okay, so with that said, hopefully that makes a lot of sense to you. Domain does not necessarily is not the same as continuity. Okay, so domain just says, is there an output vertical line that passes through a point on this graph? All right. Can you explain why an infinite discontinuity is still continuous for its domain? So that was kind of, this is Padlet question 3, but it pretty much is that same idea of basically, and I want to go through this in depth here. If I have a vertical asymptote and the function either approaches like that and like that, then on its domain, there's a right or a left. But I want to be clear, just because it has an infinite discontinuity does not mean that it's always continuous on its domain. So I want to show you an example of a, off to the side here, maybe in black here. Here is a function that has an infinite discontinuity. There's a vertical asymptote, okay? But the point is here, and then maybe we even have a graph that has a hole and it kind of does that. So there does not need to be an asymptote from both sides. Honestly, it only approaches infinity on this side of the asymptote. On this side, it actually approaches a value. But then that point is there. So this is still considered an infinite discontinuity, but this is not continuous on its domain because that X value is now in the domain. The reason this one was continuous in its domain is because the X value is not there and it's not in the domain. So this is not a question. So now, not to be uncertain for you. If this function was, if this value was in question, this is definitely discontinuous at this value. This is a jump. It's really an infinite discontinuity, but jump is a good way to say that as well. Okay? So this first question, a calculator is allowed. I really want to make sure that you're all set with putting stuff in the calculator. And I'm going to show you kind of what I expect you to do to solve this question. So I'm going to give you 5 seconds to pause it and try the question. 5, 4, 3, 2, 1. Okay, so the first thing to do is to put this in the calculator. Of course, I use Desmos because it just looks nice, but you have to use the TI calculator. So you have to put parentheses. This is again, invisible rules of math, parentheses around that and parentheses around that, and the division sign between. And I would just glance at the graph and see what it says. Holes will not show up on the TI calculator. So that's tricky. So the question did say, what's happening at x equals 2 and x equals -1? Well, so then I would use a table. When you go to the table, you can put in your own values for the input and the output should be auto. So you should be looking at, you should go to table set. Okay, so look for the blue table set. So you have to hit second in table set. And then you need to go to independent needs to be asked. And then the dependent needs to be auto. And anything that shows up when you hit table, there should be nothing that shows up. But if there's anything, you can delete it. And then you can put in any of these values and it will automatically assign the dependent variable, which uses the function. So you got to put this in your Y1 in your calculator. And then you can enter these values. Look how these values help us reveal what's happening, right? You put in -1, you put in 2. They're both undefined there. So there's either a hole or maybe a vertical asymptote. So of course, around -1, I just put in some values close to it. It does seem as though that these values are going to approach each other. You could try a few more that are close, right? But just to see the pattern of values. But this is definitely enough. And with the graph to see, okay, there's a hole there. I put this hole in, by the way. So even Desmos doesn't put the hole there. Okay. And then, of course, at 2, we see that these are just negative, like so much. I mean, these are kind of close to each other, but not close enough for me to say that they're approaching -20,000 or something like that. And plus the graph is just ever decreasing. And so this one's already beyond -20,000. Anyway, then that looks like definitely, and you can put a few more values into C. So with that said, the answer to this question is for sure D, because a graphing utility will reveal that there is, F has a discontinuity due to a vertical asymptote at x equals 2 and a removable discontinuity at x equals -1, because the function value does not equal the limit. F of -1 was undefined. Okay, next part. Question 2, no calculator here. So I'm going to give you 5 seconds. Try to do this one on your own. Of course, pause it, take as much time as you need. 5, 4, 3, 2, 1. Okay, so hopefully you have paused that and tried it. The answer is C, and this is because the question was the graph of the function f is shown above. What are all the values of x for where there's a removable discontinuity? Of course, you saw there's no point there, so this was removed. The limit still exists, but it doesn't equal the function value. Limit still exists, doesn't equal to the function value. But at 1, the limit doesn't exist. So this is a jump. Okay? But the left-sided limit equals 2 and the right-sided limit equals 0 at 1. So that would be how you can tell that it's a jump, by the way, by breaking up something from the left or from the right. So at 0, x equals 0 and x equals 2. Common mistake for some reason is people look at this as at 1 this is happening, but that's the limit value. That's not the values of x are locations. So when it says what are all the values or where are the values of x, that's going to tell you the location. So yeah, because every function passes a vertical line, every function passes a vertical line test, but So then every x value is unique in where it talks about the graph. Because at 1, for the y value, there's 3 spots it could be talking about if you said at y equals 1. So anyway, all right. Question 3, no calculator here, so go ahead, I'll read the question first. Let f be the function defined by, and that is an x to the 4th minus 4x squared in the numerator, x squared. So you're going to want to factor this, just giving you a hint. Which of the following statements is true? A, B, C, or D? Read all those statements. Pause me. 5, 4, 3, 2, 1. All right, the answer was definitely C, and here's the reason. So when I look at this function, I want to factor it, and the way that it factors, if I were to look at the limit as x goes to 0, then I can factor an x squared out and an x out. And then x squared minus 4 factors to x plus 2x minus 2. And so it looks like nothing else cancels besides an x. So the moment that x cancels, we have to remember that it was still in the original. So at x equals 0, it's undefined, for sure. You can't put 0 in. But it was really algebraically removed when you canceled from x squared over x to just x on the top. You canceled it, right? So that is removed algebraically, so that should hint to you removable. Plus the limit does exist now. Now that we have this situation, we can plug in 0, and even though the numerator is 0, because there's times x, the denominator is -4, which is fine. That limit is equal to 0. So something is happening with this graph at 0 somehow. Maybe at 0, something's happening, but there's a hole, right? So with that said, it's definitely removable because the limit existed from the left or right of 0. And then the other thing is there's a vertical asymptote at x equals 4 because that's what was left on the bottom and it didn't cancel. So that tells you that there's a vertical asymptote there. Okay. Calculator allowed for this one. Try it. So f of x is equal to this crazy function. I'll read it for you. It's x to the 3rd plus 4x squared plus x minus 6 in the numerator, 3 times sine of negative pi over 2x, and then plus 3x squared in the denominator. And they want to know what's happening at x equals 1. But you're allowed a calculator, so you should not be doing any algebra. And that's actually back to question 1. People want to start factoring this. Do not do that because question 1 said calculator allowed. The moment you have calculator allowed, you shouldn't be doing that stuff. You should be getting a graph and actually using a table here would be the best. That's what I said to do. Okay, so let's go to question 4. Okay, ready? 5. Pause it. 4, 3, 2, 1. Okay, so here's what the graph looks like. And they were talking about, what were they talking about? X equals 1. So at x equals 1, I put the hole in, but I used the table again. And this time I went to 1 with 3 values here. You can see they approach 2 from the left and 2 from the right. So the limit looks like it exists in the table, but you know 1 is undefined. But the other thing you can do is look at the graph. On your graphing calculator, you probably won't see the hole. It'll look continuous there, right? So that's all. So, but you know in the table, it's not continuous at 1 because it's undefined at 1. Okay, but now we need a good reason. So this is important. So the limit did exist for sure, right? It was 2. The graph reveals that. The table suggests it and the graph reveals it, but f of 1 does not exist. Now let's look at the other answer choices. I like to do that. Neither of these exists. Well, f of 1 doesn't exist, but the limit does, it's equal to 2. Okay, what about part C? The limit, they both exist. No, f of 1 doesn't exist. And then same with B, f of 1 doesn't exist. But this right here is how you would say it's continuous if it was true. If f of 1 plugged the hole, then it would be continuous. So this is the money right here, okay? Question 5, no calc. Let's see if you can find the step a student messed up on. So a student attempted to confirm that the function f here, that crazy function, and that's x squared plus x minus 6 over x squared minus 7x plus 10 is continuous at x equals 2. In which step, if any, does the first error appear? Looks like the first step was factoring. So you got to check the factoring, make sure the factoring is correct. Step 2, and I'm going to let you pause it soon, okay? You should just listen to me for right now. Looks like we try to compute the limit right here, so you got to check that. Step 3, we try putting in 2 for the canceled one, the canceled version of this. And then step 4, it looks like they got the same values, so they declare continuity with this beautiful statement that everyone forgets, but this is the statement that tells you that it's continuous, right? So looks like there's no errors. I'll give you a chance to pause it and try it. There is an error. 5, 4, 3, 2, 1. Okay, the error was step 3. Let's talk about why that is. So step 3, the reason is because in step 2, like when you cancel something and you're computing a limit, the limit isn't using 2, it's using negative, it's using 1.9, 1.99, 1.999, 2.1, 2.01, 2.001. But because you cancel that x minus 2, I call it the problem child. It's at 2, this is causing a big issue because you're dividing by 0. When you cancel this, you tell yourself, the moment you cancel it, at 2, it's removable in some way. Because it's canceled, it's not in the denominator anymore. I mean, if it was like an x minus 2 still down there after you canceled it, like this was an x minus 2 squared or something, then yeah, it will be a vertical asymptote. But it's gone. When it's gone, then of course you can use this function to compute the limit, because this is what the function itself models. This function itself plugs that hole. This function itself plugs that hole right there. X plus 3, put this in your calculator, put this original function in, and then put x plus 3 over x minus 5, and hopefully you have 2 different colors. You'll see it, they're coinciding the whole time. So this function behaves the same way as this one, everywhere except for 2. At 2, this one has a problem, but this one doesn't. So that's why the limit still works out just fine. The limit is definitely negative 5/3. That's correct. But the function value, you can't use this one is just telling you, yes, the behavior around 2 is going to be this, and at any other value is going to be this, but not at 2. At 2, we need to use the original function, which has a division by 0. So this is where it's undefined, and thus the limit does not equal the function value. Okay, so step 3 is the error. Step 4 is then incorrect. Okay? So now let's talk about the continuity steps. So this is going to be really important for the next 2 questions. One is a multiple choice, one is a free response. Literally what you need to do is, if you want to know if something is continuous, so I want you to understand, you learned continuity over an interval. Over an interval, you do not need to justify. The way in which you just have to declare something is continuous over an interval, because what they're going to do is give you the function. They're going to give you the function, or they're going to give you a graph. They're not going to give you a table and say prove over an interval. So over an interval, like from like 1 to 5, right? If the function doesn't have any of the 3 bad things, or the 3 bad things don't appear on that interval, it's continuous. That's it. But at a point, you need to justify with this statement. This is what this class is all about. And this is your very first really true free response situation. So sometimes you have to compute this limit first before you can make this statement, but this statement must be made if you want credit to say something. So in other words, A is say 1. They say, prove at 1, x equals 1, that this thing is continuous. So we need to take the limit as x goes to 1 of f of x. You have to remember that if it's a piecewise in any way, you're going to need to break it up, limit from the left, limit from the right. Now, the only piecewise you don't need to break it up is if you had, say, x is not 2, and then x is 2. And those are 2 parts. This limit you won't need to break up, and usually this one right here is a removable function, usually. So usually you can just compute the limit of this piece, and that's how you access the piece, is with the limit. Now, the bottom one here is usually they usually just like put a value in, right? So that's the only one you don't need to break up from the left or right. But the moment that you see like x is less than 7, x equals 7, x is greater than 7. The only way to access that top and bottom, these two right here, is to use the limit from the left of 7 of f of x and the limit from the right of 7 to access these two. And then usually these two are continuous pieces, and you can plug in 7 after you access it. And then you can declare that that limit exists because the limit from the left and right of 7 both match. And then whatever that value is, and then f of a is usually pretty easy. Usually you can just plug it in. And sometimes that middle one isn't there and the equal sign is put on one of the others. Then, of course, the limit from the left or right, one of them is going to match plugging in the function value. And that's a fine thing. That happens all the time too. Okay, next. What about this slide? So this is continuity at endpoints. Now this is a minus here. This is a from the left and this is a from the right, and that's a big difference. So one of these is from the left and one of them is from the right. I want you to pause the video and see if you can figure out, and this is how you can be continuous at an endpoint. Okay, so 5, 4, 3, 2, 1. Okay, you've paused it and you've come up with an answer. So I want you to see, to go to a just from the left, so that means that the function might disappear, but from the left, so this function's going, and it stops, and so does the function value stop there too. But there's nothing to the right. Well, this is still considered continuous at the endpoint, because to the right, there's nothing in the domain, and the one-sided limit as you go to a, which would be right here from the left, equals the function value. How we would get discontinuous in that case is something like this. If we had that, the limit from the left does not match, and this is discontinuous. Okay, so right here, this one was from the right side, so the endpoint would look something like that. So you'd be traveling from the right to A. Of course, this is A, and this one's A as well. Questions on that? Oh, I don't know why I just said that. That's hilarious. I literally say that all the time. I love that I just said that. Well, now you get to email me your questions. Okay, so the next one is a really good example with the whole piecewise situation. They're saying let f be the piecewise function defined above. Which of the following statements is false? So remember, this thing has a right and a left of 1. It has a right and a left of 2, right and a left of 3. It even has a right and a left of 4. This thing is actually, the domain is all reals, it looks like. So you can see that because, you can just go through these steps and see if there's any intervals that were skipped. Nothing's skipped. So we're all set. Everything, this is not necessarily continuous everywhere, but it's, and even though each piece is a continuous piece, if you didn't have the restriction, this doesn't mean that the overall function f, because it was cut off. So there could be jumps here. Basically, this one's gonna have a jump, if anything. So now I'm gonna give you a chance. Let f be a piecewise function defined above. Which of the following statements is false? So exactly one of these is discontinuous. Okay, 5, 4, 3, 2, 1. All right. So before I move on to the next slide, I want to eliminate some answers. So at x equals 1, we have to check this. We have to check this because that's where this function switches. But what about 2? 2 is in this interval, and this thing is continuous in that interval because there's none of the 3 bad things. And we don't need to prove anything here. This is totally gone. It's continuous there, so it's not false. Okay, it's true. And then same with 4. This is continuous because there's none of the 3 bad things, and 4 is on that last interval. 4 is bigger than 3. So from the right or left of 4, this is a line, so 4 is definitely continuous. So now we just got to check at, I'm going to show you the free response setup for this. This is super important. Now, in multiple choice land, you don't need to show work, so you can do a lot of this quickly in your head, but you need to practice free response. So if I want to show if x is continuous at 1, let me show you. Okay, so it will be this. It will be the limit as, and I know I can immediately jump to the fact that I go to 1 from the left because that accesses the top piece. So I would need to say the limit as x goes to 1 from the left, and I would start with my f of x notation. And now I'm saying to the reader, okay, I know that I'm going to be giving the gatekeeper 0.9, 0.99. So I'm going to be only accessing that top piece. And because I'm only accessing that top piece, there it is. And now putting this limit, doing this limit is just plugging in 1 because this is a continuous piece. So we pretend like it's, uninhibited. Now that we've selected it, it's like an uninhibited thing. So if you can plug in 1, then so will the values close to 1 from the left be that same value. So let's plug in 1. 1 squared plus 2 times 1 is 3. So we get 3. Then we can do the limit from the right, which accesses a different piecewise piece, 1 from the right of f of x. So then we're going to do the limit as x approaches 1 from the right of the piece that it uses. And when I give the gatekeeper values like 1.1, 1.01, it's going to give me that bottom function out. So it would be x to the third plus x squared plus x. And again, that would be a situation where we can just plug in 1. So 1 plus 1 plus 1 is 3. So far, so good. Now I do f of 1, literally giving the gatekeeper 1 only. This finally actually accesses that piece. So that would be 3. And therefore, if a free response, if I was showing that this is continuous, I would say the limit as x goes to 1 of f of x equals 3 because, and then you would have to write this. It's annoying, and this is why students mess it up. But you do have to say because the limit as x goes to 1 from the left, because this is the whole test of f of x. And of course, you use the notation, is equal to the limit as x goes to 1 from the right of f of x. So this would be in one fell swoop, we'd be writing this statement. It would be all horizontal. This whole statement here would be in one line. And that it would be justifying why the limit is 3 because both of these. So students don't write this and then they lose a point because the reader can't say that this is 3 just based on the fact that they said the limit from the left is 3, the limit from the right is 3, so therefore the limit is 3. Some graders will give you credit, but we're not gambling. So we're saying because you just got to write it out again. And now we're ready to finally say the big statement. This is free response land. So we need to say the big statement. The big statement is that, and all that you need to say here to say that this is continuous, you say continuous at x equals 1, and you can, at x equals 1, I need the at, okay? Because, and here's the statement, this is the money right here. The limit as x goes to 1 from the right or left is 3. So, but we're not going to write that. We're just going to write of f of x equals f of 1. And the students will mess up. Tell you what they'll mess up. They'll accidentally forget that limits need an x in there. And function values, doesn't have the x in there because we're really saying this limit and this limit are equal. You can't just say, you have to follow these steps. And this is what I want you to do is I want you to go back in the video where I didn't have this written and try it. Try to recreate this. And you're also going to get a chance to do it. So now let's speed this along. We did get 3, we need to go to 3 now. So the way you can do it pretty quickly here to check to see if it's continuous at 3 is plug in 3 for this one and this one. But the limit from the left of 3 is how you access this piece, and the limit from the right of 3 is how you access this. So even just right away, you can see this bottom one's a little easier. If I put 3 in, I'm going to get 7, and that's not equal to 0. So f of 3 is 0, and the limit from the right, even if this one still also equals that, it won't. I can tell because it's like 27 plus 9 plus 3. That's going to be, it's a jump. It's definitely a jump. So the answer is definitely C. And you can see where they actually computed the values out. Pause it right now if you want to check it out. Okay, you're going to pause this question. You're going to try this one now. So the amount of money raised during a fundraising campaign is modeled by the function f defined above, where f of t is measured in United States dollars and t is the time in days since the campaign began. Is the function of f continuous at t is equal to 7? So look what's happening at 7. 7 is a change, even if these are continuous pieces, and actually they are, because this one right here is discontinuous at 4, but 4 isn't on this interval. So even if it was, it's not a problem at 7, and they care about 7 here. Okay, so that was just me talking about the question a little bit. Are you ready? You're going to try to justify just like we did on the previous slide. 5, pause it, 4, 3, 2, 1. All right. So this is I think my last slide here. So this is the solution. What you should be doing is realizing you do need to access from the left of 7, and it accesses that top piece, and you plug it in, and you get 254. Now, there's no calculator allowed here, so you're going to have to do this without a calculator. I didn't say something about that. The limit from the right, and you use the function as it's named, and then you select the piece of it. Because if you forget this part, they're not going to necessarily make the connection for you that this was this function, right? So that's how tricky it can get. So you got to just start with your notation first, okay? And of course, 7 from the right, again, this is continuous at 7, 4 it's not, but I can plug in 7 and so will the limit be 7. That's what it means. Okay, so 800 over 3, and therefore these definitely don't match. So no, f is not continuous because the limit from the left and right don't match. Now, that would be the answer with reason. That is acceptable. Now, I would really rather you ended up saying the limit as x goes to 7 does not exist and is not equal to f of 7. So f of 7 is also something that we need to talk about. So this is the AP Classroom scoring, but I would have rather this, and this is how I'm going to end the video here. I would rather you have said the limit is to end the question. You did all that work, you found 254, you found 800 over 3, and you found f of 3, but I would rather you have ended the question, ended, saying this. The limit as x goes to 7 of, and you have to capitalize it. See, I almost lowercased it. Capitalize it because that's what it is, f of, and it's t, so now I actually have to go back. See, I'm all of that. And I think even that last slide didn't use it correctly. So we for sure need to use the variables that are given to us. And that t looks like an x. This is fail sauce all around. Let's try to make it good. So the limit as t goes to 7 of f of t does not equal capital F of 7. You don't need to say that capital F of 7 is 800 over 3, and you don't need to say that the limit as t goes to 7 of f of t does not exist. You have the justification earlier, so you would need, this statement would be the way you'd want to end this truly to get all the points. Okay? So hopefully that makes a lot of sense. I'm going to stop the recording. Actually, let me just double check that I didn't accidentally forget some ending slide. I think we're good. And I'm going to end this. 6 for your smart solution. Oh, yeah. So, okay. There were 3 slides I forgot. So what I want to do now is I want you to do, because you're supposed to be viewing this in class, but I want you to do the breakout rooms or just work together or work separately, whatever the teacher is deciding that's covering for me. But go ahead, and for second and fourth period, you're going to be asynchronous anyway because of it's SAT day. So you go ahead and just work on the classwork. Okay? Bye, everybody.